So we're going to use the square root property in order to solve the following equations. Starting with example A, we have 16x squared is equal to 17. So we're trying to solve for x here. And even though this is a quadratic equation signified by this x squared, and typically when you see a quadratic equation, you think maybe factoring, you think maybe putting it into the quadratic formula. We're going to use the square root property instead in order to solve this, and this is how that works. What we want to focus on is we want to get our x squared term by itself. So what I'm going to do, I'm going to start by getting rid of the 16. Remember that this is 16 times x squared, so the opposite of multiplication is division, and I'm going to divide out the 16 on both sides. That's going to leave me with x squared is equal to 17 over 16. Again, that does not simplify as a fraction. We do not want to type 17 over 16 into a calculator. That will only give us a decimal, which is not going to help us here. In order to finish this problem and solve for x, what we need to understand is when we solve equations, we typically do the opposite of what we have. Opposite of multiplication is division. Opposite of addition is subtraction. Well, the opposite of a square is a square root. And that's why we're going to use a square root in order to solve this, because to get x by itself, we need to take the square root of it. But remember that what you do to one side, you must do to the other side. So the square root of x squared cancels. They are opposites of each other. The square root cancels with the square, leaving us with x. And on the right-hand side, we have the square root of 17 over 16. And we need to know a little bit about radicals in order to simplify this. One thing that we should know about radicals is the quotient property. The quotient rule for radicals says if you're taking the square root of an entire fraction, what you can do is you can split that up to the square root of the numerator and the square root of the denominator. The reason why we want to do this is because I'm taking a look at the denominator specifically. 16 is a perfect square. So if we take the square root of 16, we get 4. So that's what I'm going to do here. I'm going to go ahead and take the square root of 16, which I know is a 4. Square root of 17 cannot be simplified. There is no perfect square that goes inside of 17. There's no way to break that down. So that just means that x is equal to plus or minus the square root of 17 over 4. You need to remember when it does come to square roots, you do have a positive and a negative variation of the answer. So it's two different answers, positive square root of 17 over 4, negative square root of 17 over 4. For example B, we have k plus 6 squared is equal to 28. So our squared term is completely by itself on one side of the equation, which is what we want. So we need to remember that the opposite of a square is a square root. Just like the opposite of a square root is taking the square of it. So if I want to get rid of this squared term here, what I need to do is take the square root of it. But what I do to one side, I must do to the other side of the equation as well. On the left-hand side, a square root and a square cancels, leaving me with the k plus 6. And on the right-hand side, I'm going to go ahead and drop down that square root of 28. And what we're going to need to do is we're going to focus on simplifying this here. So when you're focusing on simplifying radicals, remember that you are using your perfect squares. 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5, 6 times 6, and so on. What you're looking for is you're hoping to take your radical, whatever number is underneath your radical symbol there, is you want to break it up into a multiplication using one of these numbers. Now when I'm looking at the number 28, 28 is 4 times 7. So the product rule for radicals says that we can do this, that we can split it up into a multiplication as long as that multiplication is equal to that number. So 4 times 7 is 28. Let me go ahead and drop down the left-hand side for right now. The reason why we want to do this is because the square root of 4 is a perfect square. The square root of 4 is equal to 2. We can go ahead and take the square root of that and we get a 2. Now the square root of 7, that's not a perfect square. There is no number There is no perfect square that's smaller than 7 that we can use to break apart 7. 7 is only 1 times 7, nothing else. And since 7 is not a perfect square, we cannot use that. That just means that it drops down. There's nothing else we can do there. So the square root of 28 turns into 2 square roots of 7, and we do need to remember to add the plus and minus to that anytime you take the square root of anything. Which means that the only thing left in order to get this equation solved for k is this plus 6 that we have here. We're going to subtract that to both sides, giving us that k is equal to a negative 6 plus or minus 2 square roots of 7. For example C, we have 12x squared plus 48 is equal to 0. So let's focus on getting our x squared term completely by itself. In order to make that happen, we need to start by subtracting this 48 on both sides. 48 minus 48 cancels, so we drop down the 12x squared is equal to a negative 48. Divide out the coefficient on both sides, so let's get rid of that 12 by dividing it out. 12 over 12 cancels, leaving us with x squared is equal to, now over here we had negative 48, we're dividing it by 12, negative divided by positive is negative, and 48 divided by 12 is a 4. So we're left with a negative 4 here. We almost have x solved. Here we have x squared, so we just need to get rid of that square. And remember that the opposite of a square is a square root. So what we're going to do is we're going to take the square root of both sides. On the left-hand side, square root and a square cancel, leaving us with x. And on the right-hand side, let's focus on what we have here. We have the square root of negative 4. Now, we need to simplify this radical. One of the first things that you should notice about this radical is there is a negative underneath the radical symbol. And we need to remember this one rule right here. The square root of a negative 1 is equal to I. So that represents an imaginary number. Typically, we cannot take the square root of a negative number because remember what a negative or what a square root is actually telling us to do. For example, square root of 25 we know to be 5, since 5 times 5 is 25. But the square root of 25 is also negative 5, since negative 5 times negative 5 is 25. So when you're taking the square root, you're looking for a number that could be multiplied to itself. 5 times 5, negative 5 times negative 5 to get that. So I want you to think about that when you do square root of negative 4. What times itself will get you a negative 4? Now you're probably thinking 2 or negative 2. And again, you need to remember, well, we need to multiply these numbers together. 2 times 2 is 4. Negative 2 times negative 2 is 4. You get a positive 4. There's no way to multiply this to itself and get a negative number. And that's where the I comes in. So what we do is we take the square root of the negative 4, and what we're going to do is we're going to use the product rule to split up the negative from the number. So this is how that looks. We're going to split this up into the square root of negative 1 times the square root of 4. So we're essentially just pulling that negative out. So the square root of 4 here, 4 is a perfect square. The square root of 4 is a 2. The square root of negative 1 is equal to I. Also, when we take a square root, there is a positive and a negative variation of that answer. So we actually have plus or minus 2i, a positive I, and then a negative 2i.